Alrighty, so it's time for us to hop into section 2.5, which is all about algebraic tricks to solve indeterminate forms. Right. So I mentioned last time that now that we know how continuity works, we have all sorts of rules for combining continuous functions, and we always figure out that limit by plugging in values, right? Which is super great when it works out, but sometimes it unfortunately doesn't. Sometimes when we plug in, we get, even when we plug into continuous functions, we might get a 0 over 0, we might get an infinity over infinity, we might get an infinity times 0, or we might get an infinity minus infinity. And these are called indeterminate forms. All right, so these four specifically. And we have a very easy to summarize way to deal with these two, which is factor and cancel. Now, we're hiding a lot in there. Factoring can be very tricky, depending on what we want to do. But that's the brief summary of it again. These guys are a little bit trickier, but mostly we transform them into these and go from there. Right, so we'll do an example showing how we would do that as one of our problems. But that's the basic idea, and with that stated, with those four indeterminate forms on the board and that vague process of what to do, we can start working on problems, because it always just comes down to that, and it's a lot of algebra. So our first problem is going to be to find the limit as x goes to 2 of x squared plus 7x minus 18 all over 2x minus 4. Now, all of these pieces are continuous, right? Polynomials are always continuous, and quotients of polynomials are continuous, except where the denominator is equal to 0. But still, all these pieces are individually continuous, so our first step should always be to try plugging in, right? Don't assume that there's not a 0 and then go through all sorts of rigmarole before you know for certain. Plug in, make sure you get an indeterminate form, and then try these tricks, right? So we would try this. We would get 2 squared plus 7 times 2 minus 18 all over 2 times 2 minus 4. This is 4 plus 14 minus 18. This is 4 minus 4. So we do get an indeterminate form, right? So that means that we want to try and factor and cancel, right? This one's not so bad. We've got a polynomial on the top and bottom, and hopefully we remember how to factor polynomials. So let's try and do some work here. The bottom is pretty easy to factor, right? I can pull a 2 out. We've got that greatest common factor trick going on. And the top one, luckily enough for us, is a quadratic, right? So quadratics are the one that when we went through pre-calculus, we almost certainly got the most tricks to deal with them. And, well, furthermore, we have the uber trick. We have the trick to rule all tricks for polynomials, which is for quadratics, which is the quadratic formula, right? However, we don't tend to want to jump to that. That's going to require a lot of extra room, and I don't really want to deal with that, right? Our first shortcut should be to see if we can find two numbers that multiply to give negative 18 and add to give 7, right? And it just so happens that I can think of two of those, right? Positive 9 times negative 2 gives me negative 18, and positive 9 plus negative 2 gives me positive 7. So I know this guy can be factored like that. Right? It also helps secretly there that I knew that I was looking for a negative 2. Right? So maybe it's not so easy to think of all the different factorizations of negative 18, but when you know that one of them has to be negative 2, that doesn't give you a lot of other options. Right? So now that we've factored it, we can cancel. We get the limit as x goes to 2 of x plus 9 over 2. Again, we've now simplified it, so we can try substituting again. So we get 2 plus 9 over 2, which is 11 halves. That is a perfectly cromulent number, so it turns out our limit is 11 halves. Right? So for all these types of problems, your first thing you're going to want to do is to plug in, and that will either get you the answer right away, or it'll give you an indeterminate form. Right? And then if you get an indeterminate form, like one of these two, you're going to want to factor, cancel, and start the process over. So let's try another problem. Maybe a little bit trickier. Right, so we're looking at the limit as x goes to 9 of the square root of x minus 3 all over x cubed minus 9x squared minus 81x plus 729. And I'm going to go ahead and tell y'all that I went ahead and did the substitutions, right, which looks like this. And it came out equaling 0 over 0, so we can't actually do the substitution. Right? So instead, we're going to need to factor, right? So we've got two problems. One is, how do we factor the top? It doesn't look like anything we've been taught to factor before. And the other is the bottom is not a quadratic, and it's not even anything nice. And it just makes me sad, and I don't want to do it. But regardless, we're going to start with the bottom first. So the denominator. So we don't know how to factor that right off the bat. But if you remember up here, I told you that it was a little easier to factor this one if you keep in mind that x minus 2 has to be a factor of what you have there. And then figuring out the other one's pretty easy because it's a quadratic. Right? The same trick holds true here. We know x minus 9 is a factor. And if you know one factor and you want to find the rest, how do you do that? You divide. Right? So some of y'all might remember long division of polynomials from pre-calculus. If you want to do it that way, that's perfectly fine. I'm going to suggest for these types of problems, you make your go-to be synthetic division. Because this guy is always going to look like x minus c. Right? That's where I got that from. That's where I got it in the last problem. That's where you'll always get it for these. And dividing by x minus c is exactly what synthetic division is designed to do. It can do other sorts of divisions, but it's trickier to do it that way. Right? So if we recall, synthetic division means we take that c and we put it in a box. Then we take the coefficients and we put them on this top row. We put our bar down here. We drop down the first number. We multiply these two. And then we add. Then we multiply. And then we add. And then we multiply. And we add. Now, unless something went horribly wrong, we should get a 0 here. If you don't get a 0 there when doing this sort of problem, then your algebra went wrong somewhere. Either in the substitution, and this isn't actually equal to 0, or in your synthetic division, right? Because this box should always give you this number. Or not always that number, but if one of them is 0, the other one has to be 0. So that's one way to check yourself, is after you finish doing this, you don't get a 0 there, right? So this tells us that we can write this as square root of x minus 3 all over x minus 9, x squared, because we always start going 1 down from that, no plain x's, and minus 81 as the constant. Right? So we factored it, right? Not entirely, but that next one's a quadratic, and even better, it's a difference of squares. Right? So we can factor it even more and get right, because we have x squared and 9 squared, so that becomes x minus 9 and x plus 9, right? That's our difference of two squares factorization method. So that's all great. We factored the bottom. Sweet. That was looking pretty rough from the go. But how do we factor something with a square root in it? The answer is we don't, right? We're actually going to unfactor it a little bit. And we're going to do that by multiplying by the conjugate. So that should be something else you remember from pre-calculus. And we're going to multiply by the conjugate on the top and bottom because we don't want to change anything. Right? We don't want to change what this value is, so I'm basically going to multiply by 1, but it's going to be a very special value of 1. So I said conjugate and then said you should remember and didn't remind you what it was. Conjugate means when you have a sum or difference of two things. It means taking those same two things and doing the opposite thing to them. Right? So here we had a difference of two things, so the conjugate is going to be the sum of those two things. Right? It's kind of the reverse of what we did here. Right? And in fact, it's exactly the reverse of what we did there, and that's exactly why we're doing it. Because when we multiply it through, we get the first thing squared minus the second thing squared. Oops. There we go. Almost ran out of space. Right, which we can simplify to the limit as x goes to 9. Well, the square root of x squared is just x. 3 squared is 9. Okay. So, this is a trick that you can use, or that's most useful to use anytime you have something where one of your terms is a root, right? You might have seen this most often when you're dealing with complex numbers, right? Because complex numbers have I in them, and I is secretly a square root, right? That's why complex numbers have conjugates, is because they have a root in them. Right, here we just had the square root of x, not the square root of -1, but we can still use this reverse difference of squares thing to factor out or refactor that and get rid of that square root. Right, so now we can cancel some stuff out. We finally got to the canceling stage. If you cancel out everything from the top, it just becomes 1. And so now that we've done some canceling, we can try some substituting. All right, so 1 just stays 1. Here we get the square root of 9 plus 3, 9 minus 9, 9 plus 9. So we get 6 times 0 times 18, which is no good, right? But one of the things we notice here is that this is not, it's not an indeterminate form, right? This is, it doesn't have that 0 up top, right? Our indeterminate forms were 0 over 0, infinity over infinity, infinity times 0, and infinity minus infinity. A number like 1 divided by 0 is not an indeterminate form. Instead, whenever you have a number over 0, you know that the limit actually goes to infinity, or negative infinity if there's a negative number involved. So in this case, we did figure out what it was by breaking it out of that indeterminate form, and then substituting and using kind of a new trick. They sort of imply it in past chapters, and this is the first time they sort of say it right off the bat. Right? So another example along those lines. Right, if you have the limit as x goes to -2 of x over x plus 2, right, if we try substituting, then we get -2 over -2 plus 2, which is -2 over 0. This is no good, so we can't substitute, but we do know that this guy is equal to negative infinity. Right, because there's a number up top, there's a 0 on the bottom, and that number up top is negative. So we know this is going to go towards really, really big negative numbers. Alrighty, let's see. So another problem. Let's say the limit as theta goes to pi of cosecant theta over cotangent theta. And if we plug in, if we do substitution, if you remember, both of those functions have asymptotes at pi. Right, cosecant and cotangent both have asymptotes at pi. So that means that it's going to infinity on the top and bottom of that fraction, right, when we just plug it in. So that means we need to be able to cancel some things out, but there's definitely no factoring going on here, right? But there's something even better than factoring for trigonometric functions, and that is trigonometric identities. So a good first step, which is going to get you through 9/10 of the problem in this section, is make it look like sines and cosines. So if we remember, cosecant is 1 over sine. And cotangent is cosine over sine. Right, and if we remember something I talked about way in one of the very first ones that we did, dividing by a fraction is the same thing as multiplying by its reciprocal. So I can take this guy, and instead of dividing by that guy, I can turn it into multiplying by its reciprocal. Right, and that's super sweet, because we didn't actually have to do any factoring or anything. We just used trigonometric identities and canceled some stuff out. So now that we've done the canceling step, once we do some simplifying, we can try substituting again. I get 1 over cosine of pi. And if we recall from our chart, let's see, cosine starts at 1, and by the time we reach pi, we get down to -1. And so that's what our limit is, right? So we don't always have to factor, right? Sometimes we can just use our trigonometric identities, but then when we cancel is when we start back over and try plugging in and see if everything works now, right? And one last problem. Alrighty. So, if we try to just plug in here, we get 3 over 2 minus 2 minus 27 over 2 squared plus 5 times 2 minus 14, which I'll go ahead and skip the algebra I've already done, gets us 3 over 0 minus 27 over 0. Right? And if we recall from our rule before, that means it's infinity minus infinity, right? Because just some plain number divided by 0 is always going to give us an infinity, right? When we're talking about limits. So if we're taking the limit of something. And infinity minus infinity was one of those indeterminate forms that I said we're going to transform into one like this, then we're going to factor or use identities and cancel. So, how do we turn this into a single fraction, right? And the answer is common denominator, right? Anytime your thing like this comes from two different fractions and you want to make it look like 0 over 0 or infinity over infinity, that's going to mean finding a common denominator. So, x goes to 2. To do that, we're going to need to factor both denominators, but one of them is already factored, right? And again, we're using some information that we have because it's this type of problem. The fact that this gives us 0 means that x minus 2 is one of the factors, right? And then I just need to figure out what the other number is that when I multiply it by -2, I get 14, and add it to -2, I get 5. And it turns out that that is positive 7, right? And so finding a common denominator, in this case, since our denominators have a common factor, means bringing the other factor over, right? And we do that by doing the same sort of trick as we did for the square root problem and multiplying by a very special value of 1 so that nothing changes. And then I'll simplify this a little bit. So multiply through that 3. We'll go ahead and keep this factored because it'll probably be handy later. Right, so now these guys have the same denominator, and that means we can just take everything and put it under that same denominator. And so we get 3x minus 6 over x plus 7 times x minus 2. And then we can factor what we have left over there. That's 3 times x minus 2. And we've got some stuff to cancel, which means that our next step is always going to involve plugging in and seeing if everything's good. And it turns out that is just a regular old number, so our limit's going to be equal to 1/3. Right? So it turns out that sometimes infinity minus infinity is 1/3. Right? Okay, so that goes through a decent example of all the different tricks we have in this section. Next week we're gonna keep talking about different limits. I think we have one more week of limits. Rounding ourselves off with that formal definition that I warned y'all would be coming up. And yeah, so we'll be adding some tricks. One thing that this can't do, I'll go ahead and give a preview, is the limit as x goes to 0 of sine x over x, when we plug in, gives us 0 over 0. Right? So that is an indeterminate form, but as it turns out, we can't factor. There's no trigonometric identities. There's nothing we can do there, right? So these algebraic tricks that we've learned so far are really useful in a lot of cases, but they're not universal, right? They're not going to solve every single problem we might ever want to do. But the trigonometric limits is going to give us a bunch more that we'll be able to do, and that will be what we talk about next time.